Good evening, everyone, and welcome to the BS and Beer Show, where BS stands for Building Science. Tonight's topic is what's new with heat pumps. My name is Ben Bogie, and this evening I'm drinking a Berlinetta Velvet Pilsner from just down the road from me in New Haven, Connecticut. BS and Beer is an independent grassroots movement to share building science knowledge through local meetup groups, and this, our Zoom show. The brew crew and our guests volunteer our time each month to bring you what we hope is a fun and informative discussion. We encourage you to start your own local group too. For more information on how to get started, visit the bsandbeershow.com and check out our December 2022 show where we go through that topic in detail. Find the chat box icon at the bottom of the screen, post questions and comments there. Be sure that you click all panelists and attendees or everyone, whichever way Zoom shows it to you. Otherwise, Zoom tends to revert to panelists only, and we have a hard time responding to questions while we're talking. The video recording of tonight's show will be available at Green Building Advisor, and all past shows can be found there and also on our YouTube through a link at the bsandbeershow.com or just by searching BS and Beer Show on YouTube. And this evening, we would like to thank our ever steady Green Building Advisor and Fine Home Building sponsors who put this thing together and manage the back end. And honestly, we wouldn't be able to do it without them. So with that, Emily, it's over to you.
Hi, everyone. I'm Emily, architect here in Maine. Unfortunately, I'm not drinking anything cool tonight, so I put it in a cool koozie. Shout out to my buddy Josh Salinger and our Portland versus Portland thing we got going on. So I'm having black cherry seltzer. Still nothing to drink at my house. Who knew? Announcements tonight. I want to let everybody know that STIGA is going to be hosting a Build Up Women in Construction event on Tuesday, July 30th. Get hands-on air sealing and weather tight training, as well as roundtable discussion for women in the industry. There are also AIA and CEU credits included, so we'll drop that in the chat box if there are any women up in the New Hampshire, New England area that are interested in coming to that event. On top of that, the Building Science Symposium series is coming back this fall. So Travis still has 2 more dates for you guys to join in on that awesome fun. Boston on September 10th and 11th, or Chicago on October 8th and 9th. So make sure you go over to KCBS and Beer and sign up for one of the symposiums. We'll drop a link for that in the chat box as well. Plenty of other great announcements coming up. If anybody has an announcement for theirs, we want to share BS wide. So feel free to give us your information later on. But those are the events I have. So Travis, it's off to you.
Can you tell me real quick, Emily, do you have eyes on the construction instruction, women in construction? Is that coming up? Did you already mention that? Did I just miss that?
I did not. I sure do. The construction instruction, women in construction is going to be a 2-day advanced building science training. Myself and Nikki Kruger are going to be doing that. So definitely anybody who wants to talk about Southeast and how to manage humidity, we are going to cover crawl spaces and humidity and building science and hands-on training in the lab. So lots of great stuff coming. That is up and live on CI's website. So that awesome. Will be, I think, September 11th and 12th, which is why I won't be in Boston. The one symposium closest to me. But for all the ladies, come out to Denver.
That's awesome. Well, we've had yet a number of them. We'll get you up more, so it'll be okay. I was going to introduce our guest, but I think first we should go to Mike Maines because he came in right at the nick of time. You may not even have a drink, Mike.
Thank you, Travis. I did just squeal into my driveway. I am drinking a local beer, Baxter Stowaway. The first beer, the first microbrew in Maine, available in a can. Still one of my favorites. And yes, let's move on to our guests.
Fantastic. Well, I'm Travis Brungard. I'm in Prairie Village, Kansas, and that's Kansas City to everyone else in the world. And I left my drink upstairs. So at some point I'll disappear to go get my drink. So for now, I'm just drinking some ice water. And that's going to get me by as we introduce our guests. We're very fortunate tonight because we have 2 of my favorites in the industry. We've got Ross Trethewey, the founder and lead engineer of TE2 Engineering. And of course, you also know him as the building engineer on the TV show This Old House and also Ask This Old House. He's a professional engineer in various states, and he earned both the Bachelor and Master of Science degree in mechanical engineering from Tufts University, where he also played some ball. Ross lived. That's sorry, Ross. I had to throw that in. I love that you got to play college basketball. It's an envy thing. You'll explain it later. So Ross lives with his wife and two young sons in the Boston, Massachusetts area. You can find him on LinkedIn at Ross Tret or on Instagram at Ross Trethewey, TOH for this old house. Ross, how are you and what are you drinking?
Thank you, Travis, for that introduction. I unfortunately being lame-o and have water. Yeah, that's
Me too.
so I needed a little afternoon kick, and I'm at the office still. So unfortunately, we don't have beer in our fridge. Boo, boo that.
Hey, how's the leg? Are you all good? The foot, the Achilles is no longer
Yeah,
toast.
I'm back.
Woo!
I'm back.
All right.
Yep, out of a walking boot. Yeah, I tore my Achilles, but that was not fun. And yeah, but healing good. So
Or it's
did
over 40,
I'm
mister.
back, baby.
Did they reclaim the rascal, or did you get to keep it?
I get to keep it.
Nice. That's style, baby. Oh, well, who else is in style? That's Dave Hazel. Dave is the Northeast Senior Manager for Business Development at LG Air Conditioning. And, Dave's got more than 20 years of experience in the HVAC industry, specializing in high performance heat pump applications and design. He educates and develops new construction builders, architects, developers, remodelers, weatherization firms, and HVAC installation contractors, along with the passive house and building science communities. Dave holds a BS and an AS degree with focus on high quality building standards. You can find him at david.hazel at lge.com. Just send him an email. Dave, what did I miss and what are you drinking?
I didn't miss much. Kind of in this is a new format for me here, first timer. Appreciate the invite. Very happy to be here. I'm drinking a York Beach Beer Company extra special long weekend IPA. And so we're going to rock that for a little bit tonight. Later on, not while we're here talking here.
Let's get three down before Ross finishes his presentation. Let's see if we can do it. Come on, Dave.
No, this is a great discussion. I think we're gonna have a great time here tonight. So Ross is the man.
No doubt about that. Do you want to go straight into the presentation? Do you want to have anything else to go, or are we going?
Rock and roll, I guess, unless
Let's go, Ross. Do we have screen sharing enabled?
we're gonna find out.
This is where Ben fills with a clever story. No pressure.
Yeah, thanks for that. I'm really good on the spot.
Oh,
Screen sharing should be on. You should be able to share.
Okay, let's try it.
oh, it's going to detonate.
Okay, can you guys?
Don't worry, Ross.
See
It's
that?
only your first time once.
We're seeing you now, buddy.
All right, cool. Let's jump into it. So what's new with the air source heat pumps? We're talking about air to water and refrigerant changes coming up. Let's jump into it. Well, as long as my computer is working. So just real quick, high level, right? Why heat pumps? Hopefully everybody on this call knows what a heat pump is and how it works and all that good stuff. But just a quick recap, right? We're moving heat, not making heat, right? Efficiency between 200% and 500+%. Meaning I put $1 in, I get $2 to $5 worth of thermal energy out. They provide heating, cooling, and sometimes domestic hot water, which we'll talk about. Load matching, they're all just about all variable speed nowadays, the ones at least that we like. And so that means that they can modulate up and down to meet the loads of the building. So it's just like cruise control for a car. We're doing the same thing for the heating and cooling loads of the building. No combustion on site, so they use electricity, obviously, so we don't have to burn any gas or oil or propane for these to run. Because they're electrically driven, they're synergistic with solar, wind, and batteries. So as we see kind of the future and the electrification movement, heat pumps are a big part of that. And then they work with all fluid types, whether we're talking about heating up or cooling down water, air, or refrigerant, that is all compatible with different heat pumps. And we've got inverter compressors, we've got electronic expansion valves, we got enhanced vapor injection. We have a lot of technologies that have happened over the last 5 to 10 years that have really started to make these heat pumps really start to flourish. Okay. So now when we think about heat pump, we have a source side and a load side, right? So the source side is where the energy is gathered from and what goes into it. And then the load side is where the heat is being delivered in this case. And so if I put $1 worth or 1 kilowatt of energy into my heat pump, think of 1 kilowatt hour, I'm going to get, in this case, 4 kilowatt hours of energy out because I stole 3 kilowatt hours of heat from the air or the ground. So my COP, my coefficient of performance, is 4. That means I put $1 in, I got 4 units of heat energy out. And that is one of the reasons why heat pumps are really starting to gain a lot of traction. By the way, that source could be air or ground, right? So it could be the air or it could be geothermal. Heat pump options, you describe them based on source and load. So they could be air to air, air to water, water to air, and water to water. Those are examples that you see here on the screen. Here's an air to air heat pump. It extracts heat from the outside air and moves it to the indoor air. Here's an air to water unit. Here is a geothermal water to air unit, water in, air, hot air out, or cold air out through the ductwork. And then a water to water unit like this, where I put water in and I get warm water out or chill water out. And they could be configuration is either packaged or split. So let me just show you the difference here. This is an air-to-air heat pump that you see in every hotel room in America. It is a packaged air-to-air heat pump. It extracts heat from the outdoor air and moves it to the indoor air. If I take that same piece of device, I split it apart, hence the word split heat pump, I now have a, wait, if I make it small, I now have a mini split air source heat pump, right? So I'm thinking about so this on the right-hand side what's circled here, the outdoor unit, the indoor unit's connected by a set of refrigeration lines, that is equivalent to this unit right here in terms of what they do. They're moving heat through an air-to-air heat pump. One happens to be packaged in a packaged form factor, one happens to be in a split form factor, okay? Hopefully that helps give everybody an understanding of heat pumps in general and configuration between packaged and split. When people say a split heat pump or a packaged heat pump, what they mean. I won't go into too much detail, but mini splits are air-to-air split systems. We see an outdoor unit, we see indoor units, and they're connected by refrigeration pipes, right? One-to-one, multi-zone, home run style, branch boxes, all of that. We can go through pros and cons, but let's keep moving. Let's get to air to water heat pumps that are split. So I take the outdoor unit outside, I take the indoor unit inside, I connect them with a set of refrigeration lines in orange, but what do I get out of it is hot water or chilled water. That's the red and blue lines here. Here's an example of a project that we did. Here's an outdoor unit, here's another outdoor unit connected to some indoor units, and we've got some buffer tanks and a domestic water heater. But what we have effectively here is the ability to extract heat from the outdoor air or reject heat from the outdoor air. And these are connected by refrigeration pipes from this unit to this unit and from this unit to this unit. And then I convert it to water. So all the copper pipes you see is water. That's the hot water or the chilled water, depending if we're heating or cooling. All right. The next one's my favorite. This is the air to water packaged heat pump. So I take that same thing I just showed you and I put it together. And this is the outdoor box. This is the monoblock. People refer to monoblocks. What they mean is a packaged air to water heat pump. And why do I like it so much? Well, one, they can provide heating, cooling, and domestic hot water. So we're going to talk about that in a couple more slides. But they kind of like the magic bullet that gives you heating, cooling, and DHW. Might not give you all of your DHW, but will give you a lot of your the majority of your DHW. In some cases, they could give you all of it too. But all refrigerant is outdoors. All in this type of arrangement, there is no refrigeration piping from outside to inside. It's all self-contained. I think about this like when you buy a refrigerator. When you buy a refrigerator, all the refrigerant is self-contained in the unit itself. It's hermetically sealed, quality controlled at the factory. You don't have to get into the refrigerant. You don't have to have any handling of refrigerant. You don't have to add any trim charge, right? You can literally set the box outside, connected with water pipes effectively, and you're off to the races. I also like the fact that there's much less refrigerant volume in these units than there are in some of the other style systems that are on the market. And so if I look at the amount of refrigerant in this unit, it's typically 60 to 90% less than a split air source heat pump. And why is that? Well, think about it. The refrigerant in this example is self-contained inside this box. I'm not traveling 50 feet or 75 feet or 300 feet to my indoor unit. The refrigeration, just like a refrigerator, the process is limited to this box. So I might have, 1 pound in this system, where another system that is a split arrangement with the exact same efficiencies might be 5 pounds or 6 pounds of refrigerant, right? A lot more refrigerant in a split arrangement system. I also can use water piping, like PEX, copper, polypropylene, aquatherm. I can use those versus copper line sets under high pressure, right? With flare nuts and flare fittings that are prone to leak and are have to require a skilled technician to make sure those are done right. Water piping has been done for hundreds of years, and a lot of people have figured out that fitting, that connection system, whether it's a soldered connection or whether it's a mechanical press fit or a pro press or something like that. I also like that I can retrofit these into existing buildings. If I have hot water or chill water systems already at play, I can retrofit those in with this type of system, right? So there's a bunch of reasons why I like air to water heat pumps. Dave, I've been doing all the talking. Is there anything you want to jump in here?
No, I think the innovation and the lack of refrigerant inside the building is definitely getting a lot of play, both residentially and commercially. So the trend toward this type of solution is, I think, going to get a lot more focus going in the future here, especially with the new refrigerant type changeover that's occurring in the next couple of years too. We'll talk about that later on as well.
That's right.
Good stuff.
Absolutely. So what do these systems look like? Obviously, a variety of different manufacturers that are all in the marketplace, a lot of different ways of applying them, whether they're single units, multi-units, whether we have a hot tank, chilled water buffer tank, all of the different piping arrangements, a lot of flexibility there, which is what also another reason why I like it is that there's a lot of different ways to control it and a lot of different ways of designing it depending on the application. All right. Here's an example of an outdoor, packaged air to water heat pump monoblock style that has a hot water buffer tank that's providing domestic hot water preheat. It's also feeding chilled water to an air handler for cooling, and I'm feeding some panel radiators or radiant floor heat systems off of that buffer tank, and I'm providing domestic hot water through an electric water heater. That could be an air source heat pump water heater. It doesn't have to be an electric water heater. It could be an electric instantaneous water heater, right? There's a lot of different ways of arranging this. This is just an idea to show you the one way to provide domestic hot water, heating and cooling as part of an air to water strategy. So a lot of people ask about the efficiencies and what's the COP of an air to water heat pump. Well, here's an example of what that is. If I look at an air to water heat pump at different delivered water temperatures, so this is 131 degrees, this is at 95 degrees. So if I look at the different temperatures, the blue line is 95 degrees, the black line is 131 degrees. And so the difference at 5 degrees is an efficiency of 1.9 versus 2.7. That might not seem like a lot, but that's a significant difference in the efficiencies. We also get a huge amount of benefit at 47 degrees outside. I'm operating at a 5 COP versus 3.2, right? So when I talk about getting these systems designed right, a lot of times it's all about getting the water temperature and heating as low as possible and getting the cooling temperature as high as possible. And if I can heat a building with 95 degrees outside, I can have an efficiency of 5 at 47 degrees outside, all the way down to 2.7 at 5 degrees outside. So that's going to win against just about any type of other heat pump strategy that I know of that's air source driven in a building. So let's talk about refrigerant changes. So the AIM Act was introduced at the end of 2020. And what that mandated is that we're going to phase down our refrigerants. Okay. They want an 85 production in HFCs by 2036. So here is the phase down strategy right here. And here is what we're trying to get to in terms of global warming potential. This is the 100-year GWP. And so for residential and light commercial systems, as of January 1, 2025, we have to hit a GWP of 700. And for VRF systems, that 700 comes into place in January 1st, 2026. They give one more year on that. There's some debate whether these dates are going to change, but this is what's been put into place as of today. So the GWP is 700. That probably means nothing to anybody in this room, or potentially nothing to anybody in this room. But here's the way to think about it. If I look at R410A, which has been the standard refrigerant over the last 15 plus years, that has a GWP of 2000, give or take. R22, which was the predecessor of that, was 1810. To hit a 700 GWP, we have to move to a different style of refrigerant. So R32 and R454B are the next two refrigerants that are really getting considered and manufacturers have adopted to get you under the 700 GWP limit, because this one's at 675 and this one's at 466. So that is what manufacturers are switching to in terms of how they manufacture their equipment. Unfortunately, 410A systems are not compatible with the new refrigerants. So you can't add R32 or 454B to an R410A system. All right, so that's a no-go. You can't do that. I think it's very important to mention that R32 has already been used because it makes up 50% of R410A. So 410A is made up of 50% R32 and 50% of R125. They mix two synthetic refrigerants together to give you R410A. The reason they added R125 was because that's a flame suppressant. And so they wanted to make the refrigerant safer with less flame propagation. So to do that, they added a flame suppressant to R32 to make it stay as an A1 refrigerant. All right. So if I look at the standard classification of refrigerants, they're either A or B. That's toxicity. A is less toxic, B is more toxic. And then A1, 1 through 3 is flammability. So A1 is where we've been sitting for a long period of time with 410A. There's no flame propagation at 60 degrees C, and it's a lower toxicity limit. So that's where we've been. We're now moving to refrigerants that are called A2Ls, and they are lower flammability on that scale. All right. There's a lot of misinformation in terms of flame propagation. So I just want to be clear here that when they test the refrigerants, they send the refrigerant and air into a chamber, they add a little spark, and they see how the flame propagates. This 90-degree yellow angle is what a flame propagation looks like for 410A. It stays within the 90-degree threshold. If I use an A2L, like 454B or R32, it goes just outside of that cone. And because it goes outside of that cone, it's no longer an A1, it's now an A2L refrigerant. So it's not that much more flammable. It's not that much more, unsafe. If I compare that to propane, this is what propane looks like. That's a different animal, right? That's an A3 refrigerant.
And we already have pipes full of propane and natural gas running through lots of houses. So
That's right. That's right. We've been dealing with propane and natural gas for a long, long time. And so we've been able to handle that safely, I would say, overall. And so I think a lot of people get scared with this flame propagation stuff. And so it really is not as concerning as what people think and make it out to be. If I were to plot the heat of combustion and burning velocity on a chart of all the refrigerants that are available, the A2Ls fall in this category. The A1s obviously are the purple over here. And so, yes, they have a little bit more burning velocity. Yes, they have similar heats of combustion, but they're not like the R290s, propanes, and the other refrigerants, that are common in Europe and other places, right? So we're not at A3 yet. We're talking about A2Ls. So I just want to make sure that people understand that they're not as scary as some people think it might be.
Or even as hairspray.
Yeah, or R152A. Yeah, hairspray. Exactly.
The 80s are back.
and my understanding, Ross, is that as we roll out these A2Ls, and David, I'm sure you can comment on this too, the equipment itself will be coming with all sorts of safety measures in place to be doing more diligent monitoring for leaking than our heritage systems had, just because of this slight uptick in flammability. So there's going to be leak sensors in order to be a life safety measure on these pieces of equipment.
And Ben, to add to that, because of those improvements that are necessary, there'll be slight cost increases from a manufacturer's standpoint. And so the 410A equipment that's currently legacy in the field, that'll still linger for a period of time for replacements and whatnot. But the R32 and R54B going forward with those sensors, we are seeing a slight increase in costs to get that into the market.
I did not see any numbers here for flammability of CO2. Is that not worth mentioning? It was on the previous two tables. I already know the answer, but please explain why we're not talking about CO2.
Well, so we are talking about CO2 because it does have the lowest GWP of the, basically of all the refrigerants. So natural refrigerants, propane, CO2, those ones have really low GWPs, but they also introduce other challenges. So CO2 is a very high pressure refrigerant. So we're talking about maybe 1,000 PSI in CO2 systems, where if we're talking about R32 or 454B, we're talking about maybe 400 PSI. So you can see operating pressures down here. So we've been dealing with operating pressures with R22 in the 200 to 300 range and with 410A in the 400 range. So if we're going to go to CO2, we're going up to like 1,000. So our typical flare fittings on a typical like line set would not work under those types of pressures. So that's one of the reasons why. But the CO2 becomes absolutely a part of the equation in an air to water package heat pump. Because now you can put that all outside in a self-contained box connected with some water lines or some glycol water lines, and you're off to the races. So like Sandin CO2 heat pumps, as an example, like some of those manufacturers are already coming to the table with CO2, which is a great refrigerant. And propane is available in Europe, which is an amazing refrigerant as well.
But correct me, Ross. My understanding is that CO2 performs well for heating of water, but it doesn't perform so well for chilling of water. Is that correct?
It's not correct. Correct. CO2 is a much better refrigerant when we're heating water. It's not as great when we're cooling that water. Right. Right. That's true. That's true. That's why propane has been, the R290 has been the kind of the adopted go-to that we're seeing in Europe because it does much better with heating and cooling, with both hot water and chill water. There's a couple other reasons why, but that's something, but that's an A3. And so that's one of the things where we don't have all of the safety regulations in place. So ASHRAE standard 15 is the one that writes the standards for safety related to refrigerant handling. And they're not really there yet with some of these, higher flammability refrigerants. So that will come with time. And I think there'll be a day in this not so distant future where propane and other CO2 heat pumps are going to be much more readily available. But we're lagging a little bit behind, Europe and that side of things. Yeah, so I think just kind of quick summary stuff, and we can go into more slides if we want. But to me, I believe water is, as the universal heat transfer medium, that is the way that we should be distributing heating and cooling. I think that the trend is to go to that direction. I think that's inevitable. I think refrigerants with lower GWPs will continue to become part of that as part of the AIM Act with a reduction in HFCs. Generally, that means higher flammability. In most cases, as you drop the GWP, you're going to natural refrigerants that have higher flammability. So safety and other things come into place. More the reason why air to water package heat pumps outside make a lot more sense. We're already using things like R290, like I said, in Europe. The equipment costs need to come down. The stuff that we've seen come across to North America obviously has some significant costs. The early adopters are going to burden some of that, but hopefully we can get the equipment costs down. And like we say on every one of these is that we need more technicians and more training. That's paramount. We have the shortage of skilled trade. That's not helping us. There's a bigger hurdle there, but yeah, that's the high level stuff. I put on my email and Dave's email up here. If you have any questions, and we can hopefully open up the chat and get the conversation going.
So Ross, you touched on something there with water being universal energy transfer medium. And I want to go back a little bit to where you were talking about COP. I had a rather savvy client send me an email day before yesterday. It was an article from wired.com that I'll drop into the chat box about this culture that's happening over in the UK right now, where they're taking air to water heat pumps and essentially like hypermiling them. If anybody is familiar with that term, where people would kind of try and shave as many miles out of the gallon on their cars, they're doing this with air to water heat pumps by doing things like predictive weather analysis. So if they don't have to create as much heat because tomorrow is going to be a relatively warm day, they're not going to bring the tank up in the house to full temperature, which result in a higher COP because it's a lower delta between the incoming and exiting water temperatures. And what they're finding on these systems that people are crowdsourced monitoring is that they're getting 365-day averages of COPs in the 4 3/4 to 5. And that's over 365 days. So yeah, I just want to second like the comment you made. I think water is where a lot of it's heading, but I also understand, Mark Rosenbaum threw a comment up in here water is good for larger systems that are spread out. Whereas if you have a very smartly designed smaller house where you can put a single air-to-air high wall unit on the wall, that's going to be a much lower energy or much lower upfront cost to get into a very efficient system. So it's not that water is going to be the winner take all for systems, but
Right. I think, but the challenge will be that, Mark's exactly right from a distribution perspective, that as the buildings get bigger, the distribution energy costs go higher when you have to use a compressor to move that refrigerant 100 feet or 200 feet. You have to use more compressor energy to do that. And so it does with smaller houses and smaller buildings with smaller loads. There's a lot of actual equipment needs to go in to make an air to water heat pump actually work well. And so there's definitely going to be, a kind of a cost benefit trade-off there to make that work. But the other part of it is that how do you get to these higher flammable refrigerants if we want to keep them outside of our buildings and not pipe them through our buildings? And how do you deal with 1,000 psi of CO2 running through a copper line set in a house when you could be dealing with water at 12 psi? There's a huge difference there in terms of safety, risk, and I'm not sure how that's all going to get sorted out in the future.
Whereas we're battling with energy storage as we move towards an electrified grid, we have a much easier opportunity to just put a larger, cheap water tank into the home and store a ton of BTUs when we're able to produce it during the daytime when solar's prevalent, and store it so we're not having to rely on chemical storage via batteries.
That's right. That's right. So this tank right here could be sized to whatever size we need. So we can use that air to water heat pump when the time of use rates are low, or however we'd like, when solar energy is in surplus. And now with the kind of smart monitoring and demand response type of stuff, you can get into really, and weather predicting, effectively knowing what the temperature might be tomorrow. Like Octopus Energy and some of these companies are coming out with the ability to monitor weather, predict the weather, and maintain a buffer tank temperature there based on what they think the future heat load in that building will be tomorrow. On top of that, charging up the tank at nighttime when the time of use rates are low, or when solar energy is in surplus. So you have all these benefits when you have the ability to use the really efficient heat pump with the thermal battery to store it. And storing mechanical thermal energy is a lot easier to store than electrical energy, with batteries and lithium ion and all the costs associated with that.
Do we want to run into the agenda long list of questions that have been mounting?
I was going to say the list
feverishly...
is daunting like last week. 2 popular topics right in a row.
You want to start at the top, Mike, or where do we want to go? There's so much good stuff in here.
Whatever. There's a lot of them here. Let's see. I think a good one was from Todd. Why does Canada get to use R290 and we can't? Lloyd says because the American producers of refrigerants screamed fire to delay the transition to a refrigerant they couldn't profit from. Is that accurate? Is there more to it than that? Is that pretty much the whole story?
I'm sorry, I missed part of that. So what the reason they're using it in Canada and not in the US is what?
Lloyd said it was because, Todd, it's because the American producers of refrigerants screamed fire to delay the transition to a refrigerant that they couldn't profit from. So is this really about corporate greed and not what's best for the environment? Or is there more to the story?
That never happens.
Come on, Dave. Don't be tight-lipped. Yeah. We had you on because we want to know what you think.
Well, part of it, I think, is because of the legacy existing from going to R22 to 410A for so many years. This leap to this type of A2L now has been a shocker to the market. So I think a lot of distribution and manufacturers are trying to determine the best path going forward, being that it's mandated and it's a requirement globally. So how to best do that is just to rip the Band-Aid off in one go. And some are just delaying it a little bit so that they can transition their existing inventory and stock out the door and then gradually bring in the newer required refrigerants. And profits are going to end up going where the most efficient way to bring it to the market exists, in my opinion.
There is something to be said for keeping America, since this is a Canada versus America question, comfortable. People don't tolerate discomfort the way that they used to. You know, Martin Holliday's suggestion that we all just put on a sweater in the winter and shut up has not been well adopted by my clients. I don't know if you guys are seeing different things where you're operating, but yeah, there's an intolerance for discomfort that will make that a very painful transition on a number of levels. And I certainly recognize that if we don't have the equipment to make the transfer immediately, and we don't have the people trained, as Ross pointed out, to manage these new systems, we will not make that transition. So there is going to have to be a slow transition to make it work, or it won't work.
Since you brought up comfort, there are also several comments in the chat box about using this as a retrofit for existing systems. Like, how do you handle it when you can only run 95-degree water through a system that's used to 170 degrees, like a radiator or something? You know, is this going to be appropriate for people to use as retrofit situations? Or, you know, we're pro building science here. Does everybody need to air seal and insulate a whole lot more before they make that happen?
Yeah, that's a great point. So, you know, if we look at this chart, and one of the things that I'm concerned about is that somebody goes and buys an air-to-water heat pump and then basically rips out their oil boiler and then throws this thing in and says, well, you know, basically puts it in the wrong application. And so a lot of the heat emitters and a lot of the older houses are designed around 180 degrees, or sometimes less than that, maybe 160. These units will not reach, most of them at least, will not reach 160, 170, definitely not 180. So to really properly apply these units, you have to get the water temperatures down. So the only way that you can do this properly in a retrofit strategy is either have the properly sized heating emitters. So back to this, these radiators have to be sized right, or the radiant floor heat systems have to be sized right, or the fan coils, the coils that are delivering the hot air, if it's a heating, you know, hydro air system, those need to be sized right for 100-degree water or 110-degree water. Really, the lower we can get that, the more efficient the system. That's what my point is here. I can go from a 3.2 COP to a 5 COP by going from 131 to 95 of leaving low temperature. So I want to get that water temperature as low as possible to be able to heat my building. It's just, you know, basic physics. If I can get the water temperature as close to the air temperature as possible, I will increase my efficiency dramatically. And it's non-linear, right? It's not, you can see that there's curvature to those lines. And so, so if we can get heat a building with 95 degrees, we're going to be in a really good place. So what that means in a retrofit strategy is a lot of times we need to weatherize and insulate and air seal those buildings, or we need to rip out some of the 180-degree design fin tube baseboard and replace it with, you know, panel radiators or something like a modern panel rad from, from a variety of different manufacturers that are designed for 100-degree or 120-degree temperatures. Some of these even have little fans too.
Or what about a third option, Ross, where we use something like an air-to-water heat pump to do the first lift of the heating on the water, and then we just use an additional combustion appliance that we want to get away from when we're trying to retrofit old existing buildings with, so way more of the new buildings. Then we do that first lift using the air-to-water heat pump, and then you just finish taking it from the 110 or 120 up to the 160 that the system needs by using natural gas, propane, whatever's available. It's not, you know, the cure-all, but it's, you know, a heck of a lot better than where we are at the moment.
That's right. That's right. Yep. So that's how we do. I mean, in buildings where we can't, let's say, insulate well enough, air seal well enough, or we can't upgrade the existing heating emitters. If that's a challenge we're running into, that's exactly the strategy that kind of the plan B. The plan B would be to leave the existing system potentially, or potentially even upgrade that to a modern, more, you know, ModCon efficiency unit. And supplement that with the air-to-water heat pump. So like you said, it's first stage heating with the heat pump. Let that run on basically milder days. Let that run as long as it can.
Maybe it handles 70% of the load in the house. And then for the 30% where you're at that design condition, then that's when you're using the fossil fuel fired option to take that final lift.
Yeah, here in Boston, we spend 72% of the year between 37 degrees and 70 degrees. Mm-hmm. So we literally, the majority of our year is basically between, call it mid-30s all the way up to 70 degrees. That's where we spend the majority of the time. The heat pump will flourish in that temperature range. It's really only when we get down to the low ambience do you need that higher water temperature in a retrofit strategy if you're leaving the old heating emitters, et cetera? And that's where the boiler will kick in, or whatever system you have. Yep.
We don't get cooling, but can't get everything.
There were plenty of questions about cooling, so since that's where you went next, Ben, you're just like keying them up as how do you manage cooling? And when I was in architecture school, we had a mechanical engineering professor who put a dedicated outdoor air system that he was working with in our fifth year's thesis studio. And we had all kinds of alarms on the doors and the windows because you couldn't open it up because we had radiant panels in the ceiling that would drip on all of our stuff. It was super cool. And by super
Literally.
cool, I mean, it was so dry in our thesis studio, we were all sick all year long. So anyway, how do you actively manage cooling in an air to water heat pump situation?
And what kind of equipment might there be out there, David, for us to do that kind of thing?
Yeah, so the most traditional way that you're cooling with an air-to-water heat pump is using something like this, a fan coil unit, right? It's effectively a chill water coil with a condensate pan and a blower that's connected to ductwork. That's the most common way that you see it done. Those fan coil units and air handlers are readily available. There are hundreds of different, manufacturing styles that they come in. Slim duct units that are more pancake style, more traditional vertical style, horizontal multi-position. Those are all available, and that's the most common way that we see it done. If you want to go a step beyond that, there are a lot of more kind of newer products that are coming over from Europe that we've used on a lot of projects. One of them is what we call the Klima Canal. It's a trench unit, so it gets mounted in the floor, and it has a chill water coil inside of it with some fans, and it actually blows air through and across that coil. And it provides cooling to the room. Now, they're expensive units. They're not going to be for every project, but there are these terminal style units that are available that can be kind of retrofitted or installed either on the floor, into some in the ceiling, in a closet, and almost like a slim duct style approach, like a mini split, slim duct system. Instead of running DX lines to it, you're running chill water lines to it.
Another question from the box then. What do we see here? Are you bolding these, Mike? You're so good at this. Air to water systems costing a bit more than air to air. Is that correct on the cost metric side? Mark Rosenbaum mentions that on Martha's Vineyard, we're seeing the air to water systems costing a good bit more than air to air. That accurate?
Yeah.
How many factors?
Ben and I worked on a project together, actually, where we specify air to water for that project. We had, I thought, which was a tremendous design package put together for that. They had that priced out compared to just an air source heat pump, mini split style
Air
system.
to air.
Air to air, exactly. And I think, Ben, correct me if I'm wrong, I think it was twice the cost?
No, it wasn't that far. We saw about a 30% premium.
It's 30%? Okay.
A 30% premium, which, we had very forward-thinking clients that were willing to pay the engineering fees for us to explore these two options. And really what it came down to is a lot of the benefit to the client was ecological and future-proofing on the home, because it's going to be easier for them to update the system if there's ever a refrigerant change that makes their air handlers no longer serviceable. So to them, that 30% wasn't worth the value add. And that's a tough one for clients, is to like, how much is the ecological impact worth to you? That's a hard one to put numbers on. Yeah, we're still seeing that. We're seeing on average about a 30% delta in comparable systems. And I think, honestly, part of my language, a lot of that is oh shit pricing from our contractors, where these are totally new to them. And they don't know what they don't know yet until we've gotten a couple under their belts.
Yep. Yeah, agreed. Yeah, the standard HVAC technician is not up to speed on air to water at all. So we're seeing inflated costs, both because of that factor, that the unknown, but also because the equipment costs are higher, because these are new products, relatively speaking, to the US. So there's it's a twofold part. But we're seeing even higher than 30% costs in some projects.
So can I pivot us away from air to water for one question here and talk about air to air options? One of the things that we've been running into as a high performance community is seeing that as the SEER values go up on the units, the coil temperatures are going down and we're getting less latent removal from these units. Are there any technologies in the work on the air to air side that'll help us handle dehumidification better while still maintaining good efficiencies?
I mean, Dave, you want to jump in there? I'm not seeing anything on the air-to-air strategy, because of CR2, because of all the new, DOE standards there and testing protocols. We're seeing that same kind of race to just go with, less compressor energy, warming up the coils, sensible heat ratios rising. I'm not seeing it go the other way. So I'm seeing less latent load, less extraction of moisture. And more sensible cooling. So
no hot gas reheat or anything like that on residential systems, or
we're not seeing that on residential systems. No, plenty of options there commercially, but nothing on a 2-ton mini split system. We're not seeing that, or at least I'm not seeing that.
Dave, you're quiet. Jump in.
I can't say some things that I want to say right now. Let's say that.
Spill the beans. Come on, man. Let's get that R&D back
read
door
between
look.
the lines, everybody.
We won't tell anyone. We'll just put it on the internet.
Let's just safely say there are solutions in development that look very promising to address that reheat and utilizing hot gas split coil kind of a potential there. So I can't go any further than that at the moment, but there is hope on the horizon. I'll put it there.
That's exciting. That's exciting.
And numerous manufacturers too, not just the one I'm currently with. This technology, there's a need there seen. So there is a race kind of trying to get the best, soonest, most efficient and effective to the market as possible. So it is a slog though, because adoption, people don't like change oftentimes. And when they do, they finally get it. And then it's a hockey stick kind of a adoption rate that occurs once these things are in play. But I'd be just a little more patience and let's see how this shakes out.
Mm-hmm. Yep.
This is more of a comment, but I'd be curious if you guys agree. Mark Rosenbaum states that the best place for air to water heat pumps first is larger systems with lots of zones. His personal house has an air to air system with 25 feet of line set. In a case like that, it wouldn't make sense to go to air to water. Would you guys agree with that?
I would agree. If you think about air to water heat pumps, they almost all will have a buffer tank, right? They're all going to have some pumps. They're going to have an expansion tank, right? So there's more indoor components that are required with air to water systems. So in a smaller house, you need a home for all that equipment. So that's a hurdle that it needs to be overcome.
True. And
the second thing is a big part of that is that when you talk about really short line set runs, that's where an air to water heat pump doesn't shine. An air to water heat pump shines when you get low water temperatures delivered across multiple zones across a larger building, where I'm trying to minimize the amount of compressor energy. And if I have to use my compressor to move the refrigerant through piping longer distances, that hurts VRF and air to air heat pumps. But that helps air to water. So air to water shines with multi-zone arrangement systems and with bigger and longer runs. With 25-foot line sets in a small home, it's a big hurdle to get air to water applied into that type of building. Yep.
Something we didn't touch on yet, Ross, that I think is an important distinction in air to water systems is the two different types. Are we doing 2-pipe or 4-pipe systems?
Mm-hmm. Yep. So we're a big proponent of 4-pipe for a lot of our projects because we have a lot of projects that need heating and they need cooling. For example, We might have really cold nights where we need heating, and the next day we might have a tremendous amount of solar gain, beating down on our buildings through our windows, et cetera, and warming up that building really fast. And so there are situations where we don't want the heat pump to heat a tank at nighttime and then race to cool it down in the daytime, right? We don't want that heat, cool, heat, cool, heat, cool. Literally, that's energy wasteful. So what we like to do, if we can, is put in a 2-tank system, a hot tank and a cold tank. We use the hot tank as typically a preheat for our domestic hot water and the ability to heat our building. And we have a cold tank that stores that chilled water, so we don't have the flip-flopping back and forth, and that chilled water can be piped to the chilled water air handlers that require cooling. That, to me, is the best way to do it. Now, that is expensive, and that adds a second buffer tank. But the advantages there, I think, outweigh the pros and cons. I think are there for it to be to go with the chill water buffer tank. The other thing about a chill water buffer tank is that you don't always need that secondary chill water buffer tank. It really depends on the volume in the system. So if you have enough volume in the system, then you don't need the buffer tank. The buffer tank's there to make sure you don't short cycle the heat pump. You don't want to turn it on and off, on and off, on and off. You want it to actually run. And so if you have enough thermal mass in the system, enough fluid volume in the piping, then you can, if you have enough, you can run the cooling system without a chill water buffer tank. But in smaller houses, you don't always have the volume, right? And so that becomes a challenge.
We're also seeing multifamily applications, new construction. This could be a better solution for the air to water solution overall.
Well, I think so to a point. It really depends on how that building is being built, right? If you're going with a centralized heating and cooling strategy that's on a kind of an owner-occupied, meter, then I think that is an option. But where you're getting into multi-condoized buildings, I think that's going to be a challenge because each one now needs its own heat pump, and therefore you have a lot more pieces of equipment on the roof, a lot more buffer tanks, you have a lot more systems that take up a lot more square footage, and most architects are not going to be happy about giving up all that space. So unfortunately, in Massachusetts, we don't allow individual BTU metering on a tenant by tenant basis or on a apartment by apartment building, which you can do in other parts of the country and other parts of the world, of course. But certain states and certain areas don't allow that. So we don't see that as a benefit, at least in our backyard.
I was just nerding out on BTU meters last night at like 11 o'clock. Better hobbies. What about storage in mediums other than water? So storing, there's all sorts of stuff bubbling up. What's out there? What might it do?
Yeah, so I mean, obviously, water is tremendous from a thermal from a BTU battery perspective in terms of BTU per pound and the fact that it's safe and non-toxic. But we are seeing it's already been, these things have been around for a long time, but phase change materials, right? PCMs, those have been around for a long period of time, and there are a bunch of manufacturers, especially more startup early stage companies, that are experimenting with different styles and types of PCMs to try to basically get that thermal battery as small as possible, but still store an equal or more BTUs than you would per unit volume. So like, think about, instead of putting an 80-gallon buffer tank in my house to store my hot water, if I can put in a 40-gallon buffer tank that's filled with phase change material that equals an 80 or a 120-gallon buffer, that space savings could be tremendous in a typical house or in a typical arrangement. So I think PCM will become, I think, we'll see how that kind of unfolds. There's definitely trade-offs with PCMs. Some of them are toxic, of course. Some of them are, of course, the ones that we like, and try to gravitate towards are the non-toxic ones that are safer for the environment. But I'm excited about the PCM, kind of the next stages of that in the future, for sure.
They also have lifespans, some of them, so it's not like an indefinite thing like a water tank. As long as the water tank doesn't spring a leak, it's still good. Some of those phase changes lose their
It's the same thing with lithium ion batteries for solar systems, right? They all have a depth of discharge and a cycle rate where they start to degrade, just like any cell phone battery, right? And so you have that same degradation that's going to affect PCM. So everything has Achilles heels, right? There's always a pro and a con, or pros and cons associated with it. But phase change are definitely exciting, and I'm curious to see where those go. There's been a lot of companies that have been playing around with that. So we'll see.
I just like that you didn't wince when you said they all have Achilles heels. Like I feel like that would still be like a too soon joke, too personal. But you're so smooth with it, Ross. It's impressive.
Yeah, I'm reminded of it, but I can't wince it anymore. So, but thank you for bringing it up again. Thanks for that.
I got to keep going because next time I see you, we're going to have to hoop, and I might have a chance if you're still injured. And if you're well, then I'm screwed.
This seems like a relevant question for those of us in cold climates anyway. Matt asks, many current ATW units can operate below -13 and even -22 Fahrenheit. However, the test standard doesn't reflect those conditions at 47 degrees in heating, and therefore the units cannot be labeled cold climate or be listed on the NEEP database. Is there a timeline to revise the standards, as that becomes a significant barrier to adoption? And a related question from earlier was something about, are these ever going to be eligible for tax rebates?
Yeah, so I'll start with the second part of that question. So rebates, like for example, the Mass CEC has rebates or some rebates available for air to water heat pumps. So that's a really good starting point. And there are different entities around the country that are offering rebates, but it's definitely not like your regular split air source heat pumps, your traditional mini splits, et cetera, and VRF heat pumps. Those get all of the rebates right now and all the credits. So air to water is definitely lagging behind. Dave, do you have anything to add on that?
Well, NYSERDA has some rebate programs that you're accurate with that description.
Yeah.
I won't add to that. That's good.
Okay. Yeah. So it's
the first part of the question, though, I didn't. I don't think I would know an answer to that one, Ross. You may be able to weigh in better.
I'm sorry. What was the first part of the question?
Because basically because ATW units are rated at 47 degrees in heating.
Mm-hmm.
They can't be considered cold climate on the NEEP database, which is the Northeast Energy something other performance probably database.
Yeah.
Yes.
I'm not sure why. I'm not sure if NEEP is going to update their standards. That's a great question. I don't know. I hope that they're going to be updating their standards. It's hard to put split source air source heat pumps and air to water heat pumps on a quote unquote level playing field because the test standards are different, right? One's a completed system, let's say with an outdoor unit, indoor unit, refrigeration pipes between them. Air to water is basically pumping water, but it doesn't have a other end of the equation in that test standard. And so you look at the air to water units, they're measured on terms of COP and EER, where if you look at your regular mini split heat pumps, they're measured in SEER 2 now, and HSPF, as in addition to COP and EER, if you want to get those data points there. So, but they're tested under almost like different standards. So they're really hard to compare on a level playing field. And we deal with this every time we spec a lot of air to water heat pumps, and every HERS rater comes back to us and says, okay, I've never seen this unit before. I don't have an HSPF and a SEER 2 rating. They're not in our database. How do I model this unit? Right? So like there's multiple kind of things that the industry needs to change. Part of that is, the HERS ratings and all the software programs need to have these input into the database. We'd love to be able to have a testing standard that puts them on a level playing field, which we don't have right now. I don't know how that would shape up. Someone much smarter than me will have to figure that out. But it would be nice to be able to have a way to compare, an air source heat pump that's a split style, mini split style to an air to water style, right? That would be great. But that's not there yet. And so I think if you try to put it and apply it to a split air source heat pump testing standard, it won't be able to really compete. It won't look right. And they won't even have an HSPF 2 and a CR2 rating. It doesn't exist.
It's 7 o'clock. I don't know if we answered even like a third of the questions that are on
Nope.
on the checkbox, and
I'm trying to scroll through them, but the messages keep stacking up here.
Oh, I'm at least 41 messages behind. I saw some comment about Penn State. We are Penn State, for my people in the audience. And then I lost everything after that. So,
It's 45 minutes ago, Emily.
I know I can't do both. I can't listen to Ross and Dave talk and read the chat box at the same time. That's a Mike skill. It's not an Emily skill.
Seems there's a lot of banter back and forth in the chat amongst attendees here versus questions.
Yeah.
Yeah.
That's the beauty of the building science community. Everybody helps each other. We have a very intelligent and informed viewership, and so it is really nice to have that. But if we have this much interest in this many questions, we may have to schedule yet another follow-up bring you guys back and go again.
Heat pumps are a really hot topic right now, and I think that this is huge. And I know I had some air to water questions that I didn't bother answering when I saw the number of other questions that were on here. So I am in favor of doing a follow-up show.
I'll lend one more comment to we haven't touched at all, but the cleaning of the indoor evaporators on these air-to-air heat pumps, certainly. I can't stress enough how important that element is in a routine maintenance and cleaning of the evaporator coils and the blower wheels inside. And if anybody took a flashlight, looked up inside there on occasion and saw what was up in there, they'd be calling a tech out tomorrow to get that clean. So don't neglect that, folks. Be sure you're working with clients that understand routine maintenance is a very important factor, and warrantying equipment by manufacturers is also, and that also comes into play too.
Great point.
Just threw that in there because
But Dave, they cleaned that cheesecloth thing that's in front of the coil, right? That works.
yeah, that stops hippopotamuses and alligators and big chunky things in the air.
Yeah.
There are no biscuits in my system. They're biscuit free. Oh,
It's like
goodness.
those bird filters that are blue that you put in your vent system and catch the cat. It's good.
The marbles from the kid. Yeah.
Yeah, it's perfect. It's perfect. But that's a great way to finish up our show. There's no such thing as a zero maintenance house. That means there's no such thing as zero maintenance HVAC. So
Agreed.
Yep.
We can't thank you guys enough for coming on and educating us. As always, it's a pleasure to talk to you both. I'm not the host. Someone else is closing us out. I was just moving it
technically
along.
Ben's
Thank
the
you.
host.
Hey,
Wait,
Ben,
what?
wrap us up.
All right. Thank you, everybody. I hope everybody has a great week, great month, and don't melt out there.
See y'all again in August.
Thanks, everybody.
See you
Thank
next
you.
time.
All right,
Great
thank
to
you,
be here.
everybody.
Thank you.